All right, let's dive right in. We're going deep, right into the core of the operating system to talk about one of its most powerful and, frankly, coolest features, kernel modules. We're talking about how you can extend the very brain of your computer, the kernel, without having to, shut it down for surgery. So think about it. Your operating system is this incredibly complex machine, right? It's running pretty much your entire digital life. What happens when you want to add a new capability? Like, say, support for some brand new piece of hardware you just bought. You can't just stop everything. That's just not an option. And that is the exact problem kernel modules were invented to solve. Okay, so to really get how this works, we first have to wrap our heads around the OS's fundamental design. The best way to think about it is like a kingdom, and this kingdom is divided into two totally separate worlds. Each one has its own set of rules, its own privileges, a completely different way of life. So on one side, you've got user space. This is where all your regular apps live, your browser, your music player, you name it. They have pretty low privileges. And look, if an app crashes, it's annoying for sure, but the system itself is totally fine. But then you have the other side, kernel space. This is the inner sanctum, the VIP lounge. This is where the OS core itself is running, and it has total unrestricted power. We're talking direct hardware access. The stakes here, they couldn't be higher. A single bad line of code doesn't just crash an app. No, it can bring the entire system to a dead stop. So, with this super high stakes, super protected space, how in the world do you safely add new features? You can't just let any old piece of code walk right in, right? The solution is to treat it like a special guest, a guest who's been vetted, who has all the right credentials to get past the bouncer. And that special guest, well, that's our kernel module. At its heart, it's a piece of code that the kernel can dynamically pull into itself while it's running. The best way to think of it is like an authorized plugin for the operating system. This is what lets us add things like device drivers or new file systems on the fly without the massive headache of recompiling the entire kernel and rebooting the machine. It's really the secret sauce for making a system flexible and extensible. Okay, to really get a feel for how these things work, let's roll up our sleeves and break down the simplest possible module you can make, the classic Hello World. We're going to dissect its structure and see what makes it tick. Look at the essential parts of its little mission. First things first, every module needs a front door, right? An entry point. That's this initialization function, which we're calling hello_init. Then you see that module init line? That's basically us telling the kernel, hey, when you load this thing up, this is the function you need to run. The job of this function is to get everything set up, to register itself with the kernel. It's literally the module's way of knocking on the door and saying, hello, I'm here, and this is what I'm bringing to the party. Now, just as important as showing up is knowing how to leave gracefully. That's where the exit function comes in, which we've marked with module_exit. You can think of this as the module's cleanup crew, and its job is to undo everything, and I mean everything, the init function did. It has to unregister every interface, release every resource it touched. Because if it leaves even a tiny mess behind, the whole kernel could be left in a really unstable state. This cleanup has to be absolutely perfect. So you might be wondering, how does a module even talk to the outside world? Well, here's the catch. It can't just use the standard printf function we all know and love. Why? Because it's not connected to the standard C library. It's living in its own isolated world. Instead, it has to use the kernel's own private version, called printf. This function writes messages directly to the kernel's log, and that's exactly how we're going to see our hello world message pop up. It's pretty much the module's only way to speak. Okay, and now for something that's actually pretty fascinating. The paperwork. Turns out the kernel is really particular about the guests it lets in. Every single module has to declare its license, using a little macro just like this one. And here's why it matters. If a module doesn't declare a free GPL-compatible license, the kernel basically puts a big red flag on itself. It taints itself. This is a signal to all the developers out there that a proprietary closed-source guest is in the house, which can make tracking down bugs a whole lot harder. All right, so we've got our simple module all designed in theory. But before we even think about deploying this thing, we need to have a serious talk about the world it's about to enter. Kernel space is not a friendly place. It's got a very different set of rules of engagement. So just how different is it? Well, first off, it's incredibly constrained. Forget about your standard libraries. You only get to use the kernel's own internal functions. Your stack space, it's tiny. We're talking as small as 4 kilobytes sometimes, which forces you to be ridiculously efficient with memory. You can't even do floating point math easily. But the most important rule of all, there is no safety net. No try-catch blocks to save you. One tiny mistake, one null pointer, and you can freeze the entire machine. Game over.
Okay, we get the code, we get the risks. So how do we actually get our little mission from a source file into the running kernel? Let's follow the journey, step by step.
The whole process basically breaks down into 4 key steps. First, obviously, we write our C source file. We've already seen what that looks like. Next, we create a special makefile. It's often just one line, and its whole job is to hook into the kernel's own build system. And this part is absolutely critical because you have to compile your module against the exact source code of the kernel you're running. This makes sure everything is compatible. The final result of all this is a file ending in KO. That stands for kernel object. This is it. This is our payload. So, with our .co file ready to go, the final step is to actually load it into the kernel. You got to be the super user for this, and you run the insmod command, pointing it right at your module file. That one command hands our payload over to the kernel. The kernel then links it into its own private world, its own address space, and calls that hello init function we wrote. And just like that, the mission is live.
And then we check the logs, and there it is. Hello world. That's our confirmation. Tucked away deep in the system log files, our message appears. That tiny piece of code we wrote is now officially a part of the operating system, running with the highest privileges possible. Mission accomplished. But hold on, the mission isn't truly over until the extraction is complete and clean. Using the aramod command, we tell the kernel, hey, we're done here, this module's services are no longer needed. The kernel does a quick check to make sure nobody's currently using the module, and if the coast is clear, it calls our hello exit function to start that all-important cleanup process. And here's our final confirmation. The goodbye message pops up in the system log. This tells us our module has done its job. It successfully unregistered everything, cleaned up after itself, and has been completely wiped from memory. It's like it was never there. A perfectly clean operation, leaving the kernel exactly as we found it. When you really think about it, kernel development is kind of the high-wire act of the programming world. It hands you this incredible power to extend the very core of the OS, but in return, it demands absolute, uncompromising precision. And that really leaves us with a fascinating question to chew on. If a single line of your code could bring down the entire system, how would that change the way you think about programming?